All right, these are some more questions, starting with chapter 2 questions on the exam review. This is page 207, number 9. This question is similar to what you're going to have to do in the exam. It's going to ask you to find the domain and range of a function. So this function, the domain is, I'm going to use interval notation, negative infinity all the way up to negative 1. And it's a closed circle, so I'm going to include negative 1. And also from 1, including 1, all the way up to positive infinity. So there's my domain in interval notation. My range then goes from 0 to positive infinity. And I can include 0 because that's a closed circle. So it includes 0, but all the values above it are in the domain. Okay, so there's my domain and range. Okay, here's another one where we find domain and range, and then we also find these indicated values. So first of all, the domain. The domain is negative infinity to infinity here. I can stick in, all real numbers are defined. Negative infinity all the way to positive infinity. The range looks like we don't have any values below here for the y values, so it'd be negative 2, not including negative 2, all the way up to positive infinity. Now, the f of 2 is, if I plug in 2, I get 0, right here. F of 1, when I plug in 1, I get 1. F of 3, when I plug in 3, I get 2 for the y value. And if I plug in negative 1, I get 2 for the y value, just from this graph. So, you know how to do problems such as those. Okay, let's try another one similar to what you'll see. You're going to have to determine if functions are increasing, decreasing, or constant. And so this is a piecewise function. It even gives us the function here. It says it's a line x plus 3 for when x is less than 0. Then it's the line x equals 3, y equals 3 for in between 0 and 2 here. And then it's the line 2x plus 1 here whenever the x's are bigger than 2. So it's 3 different lines basically. Okay, well, we can say the function's increasing. It's increasing here and here. And so to say that in x values, then we'd say here to here, right? Because we're talking about the x values where it's increasing. So that'd be negative infinity all the way up to 0. Okay, and you can include 0 in that interval of increasing. And then from 2 all the way up to positive infinity. I guess we won't include 2 because it's undefined there, but won't be super picky about that. Try not to be anyway. Decreasing, then it's not decreasing anywhere. No places where it's decreasing. Constant is the last thing we need to communicate. It's constant here in this range from 0 to 2. And you can include both those endpoints because it's the same value at those endpoints. So it's still, all the y values are still 3 at any of these points. You also have to do the composition of functions. I don't think I'm going to ask you to find the domain and range of the functions. Let me double check. So let's just we won't find the domain and range of these. Turns out that you just switch the domain and range. But let's go ahead and find the composition. So, f composed with g. What that means, this is the same thing as g of f of x. These are equal. And for part b, this is the same thing. So you always work your way inside out. You know, you do, so this f composed with g, it means you evaluate the function of g and plug that into the domain of the function of f. So I like this notation better, but this is what's going to be on the exam. It's composition notation here. So what this means is f composed with g of x, for example, is really equal to f of g of x. This is the notation I like right here. In which case you take g and you plug it in for the x's here. Okay, so it's going to be cube root of x plus 7, and then that's cubed because it goes in right here for this x, and then I need to subtract 4. If I simplify that, it turns into x plus 7 minus 4, which is equal to x plus 3. So this composition, f of g of x, is equal to x plus 3. So I guess I could write that here. F of g of, just to summarize. Okay, that's part A. Now part B wants us to do g of f of x, which I like to write like this. Okay, now we're going to plug f into g. in which case, so f goes into g now, so this function is going to go right in for that x. So I take f, which is x cubed minus 4, plug it in right here, so it'll be plus 7, and then I have the cube root of the whole thing. There's the x that I plugged in f for. Okay, so I can simplify this as x cubed plus 3, all cube rooted. And I cannot simplify this any. So here's my composition g of f of x.
Why can't you square it?
Okay, you are going to have to find the average rate of change of a function from x1 to x2. So here's a function, it's a quadratic, and we need to find the average rate of change. Well, that's just slope between these 2 points, so I'm going to plug in 1 here. If I plug in 1, I get an order pair of, let's see, 1 squared plus 12 minus 4 is 9. And then 5 would be 25 plus 60 minus 4, so that'd be 81. So there's my 2 order pair. If I plug in 1, I get this point. If I plug in 5, I get this point. All it's asking for is the average rate of change between these 2 points, which is just slope. So it's 81 minus 9 over 5 minus 1. You know, y2 minus y1 equals x2 minus x1 for slope. You remember this from algebra and geometry? Okay, which gives us 72 over 4, which is equivalent to 18. So the average rate of change is 18 on this parabola. If you look at this parabola, it looks something like this, and you can see from 1 to 4, it's pretty steep. So it's going to have a nice steep 18, up 18 over 1 for the average rate of change. All right, know how to convert English to math. For example, this says z varies jointly proportional to the square of x and the cube of y. Now we can put a constant there because that way we can say equals. Otherwise, we'd have to say varies proportional like that. So it's equal to k, whatever the constant is, we don't know. But it's proportional to x squared, square of x, and the cube of y. Okay. Other ones like this, Newton's law of universal gravitation says the gravitational force between 2 objects of masses m1 and m2 is directly proportional to the product of the masses and inversely proportional to the square of the distance r between them. So this would be the formula that we would write. So know how to convert English to math. Okay, know how to do long division. So this is x squared plus 0x plus 1. I'm going to divide that into 3x cubed plus 0x squared plus 4x minus 1. Okay. So multiply by x squared to get x cubed. That'd be x times x squared gives x cubed and make it 3x. 3x times x squared gives 3x cubed. Follow through now. 3x times x gives 0x. And I'm sorry, 0x squared. 3x times 1 gives me 3x. Now I can subtract. When I subtract, I get 1x. Drop down to negative 1. What would I multiply by x squared to get x? Nothing. That doesn't make any sense. So this is it. This is I can't multiply anything by x squared to get x. So this is the remainder. Okay, so it'd be, I'm going to write it as quotient plus remainder divided by divisor. It'd be x minus 1 over the divisor, which is x squared plus 1. So this is actually the quotient. It's actually the answer. When you do this division, you get this, which makes sense. It's a linear. You don't need a linear factor when you divide a cubic by a second degree. This is kind of a weird one. But know how to do long division. You might want to practice the next question, number 7, as well. Okay, also know how to do these statistics problems where you have a table of values for the year and salaries of baseball players, the Chicago Cubs from 2004 to 2008, where T equals 4 represents 2004. So we'll write that here. And then it says use regression feature to get an equation that fits the data, and then how well does this model represent the data? That's the R value. So we're going to take out our calculator, and we're going to plug this into stat edit. We're going to enter in L1, we'll enter in these X values, L2 we'll enter in the Y values. Once we get those entered in, we'll hit stat, we'll do calculate. This is going to be linear regression. And I like to store the regression equation in the y1 by hitting alpha zoom. I'm sorry, alpha trace y1, and then hitting calculate. Just so if I need to do any predictions later, that will help me with predicting a future value. But it gives me the R value because I have my diagnostic turned on in the catalog. So second catalog diagnostic on will give you this R value, which is 0.989. That means that's a really good fit. So how well does the model represent the data? It means it very well. And also the equation then is y equals 385x plus 115. So there's the model that represents the salaries going up about 150. I'm sorry, going up 385 every year, and it fits. It's a pretty linear model of salary growth. Okay. Know how to take a rational function and find any asymptotes. Okay, state the domain and range as well, so we can do that. It's good practice. The domain is always all real numbers, but in this case, x can't be -2. So I'm going to say negative infinity all the way to -2, not including -2. Then -2 all the way to positive infinity. I got to throw out that -2 because when I stick in -2, I get a 0 in the denominator, which is undefined. Okay. The intercepts, let's skip that for now. We already did a previous problem where we found intercepts. That's just where you plug in x. That will give you the y-intercepts. We plug in 0 for x. And the x-intercepts come when you plug in 0 for y. Okay. But let's define vertical and slant asymptotes. Okay, vertical asymptotes. These occur at places where the denominators. So because this doesn't factor in a way that this would cancel. Actually, this factors into x plus 5, x minus 2 in the top, and the bottom is x plus 2. But these don't cancel. So this isn't a whole. This is actual. This is an asymptote. Vertical asymptotes occur as zeros in the denominator. So x equals -2. That's a vertical asymptote because that's a 0 in the denominator. Okay. Let's also find any slant asymptotes. Slant asymptotes only occur if you look at your formula sheet. If the exponent's higher at the top, then there is no asymptote. But the end behavior asymptote is the division of the numerator and the denominator. So let's use that information about horizontal asymptotes here. The exponent's higher in the top than it is the bottom, so we actually have to do the division. Right? Now, I'll do synthetic division instead of long. Well, I'll just do long division again. It doesn't matter. But x squared plus 3x minus 10. So what would I multiply by x to get x squared? That'd be x. Follow through, and then subtract. Okay, that gives me just x left over. Okay, and then what would I multiply by x? So I'm going to bring down the -10. What would I multiply by x to get x? That'd be 1. 1 times x is x. 1 times 2 is +2. When I subtract, I get -12. So the remainder is -12 here. So basically, when I do this division, the function, I can rewrite it as x plus 1 plus -12 over x plus 2. This is basically the same thing. I did the division and I got this quotient, plus remainder over divisor. So this original function is equal to this function right here. What that means then is the end behavior asymptote, or the slant asymptote, is equal to y equals x plus 1. Because I don't care about this, because as x gets big, this goes to 0. I don't care about this, but the x plus 1, basically this function becomes this as x gets big. Okay? So that's, I don't care about plotting additional points to sketch the graph. I do care. You can graph it on your calculator and see if the end behavior asymptote is that line. In fact, I'll graph that line too. Okay, so here's the graph. You can look at it in your calculator. And you can see the end behavior asymptote, x plus 1. Over time, the function approaches that asymptote. So that's the end behavior or slant asymptote. It also has the vertical asymptote of x equals -2 as well. Okay?